It'll save it somewhere. I'll find it. If somehow that doesn't work, I'll have this page that I can share you. Okay, so
Okay.
you were asking how do you know it's homogeneous? And I said, and you nailed it, right? The terms all have to be the same. But look at this one right here. What are the terms? What are the degrees? What's the degree do you see?
2. It's
Yeah,
a degree of 2.
yeah, when you FOIL it all out, everything's 2, but it's not homogeneous. Why?
Because there's nothing with that.
Yeah. And so what happens is this is the first kind of substitution, kind of the most basic kind of substitution that we see in that section. We just straight up go V equals, well, let's try it this way. We just straight up go V equals 4x plus y. And then you'll have your dv dx. Or sorry, yeah, you'll need
Y equals.
y equals 4 minus vx, and then you can find your dy dx,
Mm-hmm.
right? So you end up with dv dx minus 4 equals v squared, right? And that's
Mm-hmm.
super simple to solve. Because I should probably be just a little more.
Are we going to integrate both sides of that to solve?
After you separate it, right?
Oh, yeah, okay.
Yeah. And this guy's going to require probably a differential equation. I don't think this one's hyperbolic, or not a differential equation, partial fraction decomposition.
Oh, okay, so that's going to end up being 1 over v squared dv equals, oh, see, wait a minute.
Remember this? Remember, you would take it, we're just
Oh,
focused
yeah,
on
that's the difference of squares.
yeah, difference of squares. And so we know it's going to break down into something over v plus 2 plus something over, plus a different something over v minus 2. Okay, so
Yeah.
so you got to figure out what a and b are, and then that becomes your left-hand side of this integral right here, right? And both of those would be integral. Do you want to go through, find it? You want to finish this one up, or what do you think?
Yeah, let's finish it up.
Okay, so this is we're doing the partial fraction decomposition.
Yeah.
You still with us, Becca?
Yes, I'm with you.
And so the trick is, the first step is to multiply this whole thing by v plus 2, v minus 2, just to give us a simple non-rational equation, right? Rational expression equation. So we end up with 1 equals a times v minus 2 plus b times v plus 2, right? All the fractions will cancel out.
Mm-hmm.
And this should be an identity. This should be true for all values of v, right? And so we get to choose some values of v, and we choose them carefully. We let v equal 2 and plug that into that equation. And when you plug it in, you end up with 1 equals a times 0 plus b times 4, right? And that term disappears. So that just gives us that b equals 1/4. Okay, that's good. We would come over here and we would say, oh, that thing right there is 1/4. What do you want to choose? What do you want to choose next for V?
-2.
Right, -2. So that's going to give us a -4a plus b times 0. Did I get that? Yes, -4a. So that tells me a equals -1/4. So moving up, let's remember where we were. We were finding, we were rewriting this expression, 1 over this expression. We'll put a 1 in there.
A equals -1/4 on that right side at the bottom of your screen.
Yes, so we can put, you're talking right here?
Yes.
Yeah, so we could write this like this. We could say, okay, our expression 1 over v plus 2, v minus 2 is -1/4 over v plus 2, which is the same as -1 over 4 v plus 2, plus 1/4 over v minus 2, which is the same as 1 over 4 v minus 2. We could write it like that. I'll let you guys scream at me if that doesn't make sense. But probably it's just cleaner to factor the 1/4 out and write it as 1 over v minus 2 minus 1 over v plus 2 as our left-hand side. So our left-hand side is this. Our right-hand side is dx, but we're going to move the 4 over, right? We want to get as much away from the v side, the left side, as we can.
Do we need a DV on that left side, Doctor?
Yes, we do. Good.
Okay.
Yeah, that was originally there. So we need a DV there, and then that gets us here. 1 over v minus 2 minus 1 over v plus 2 equals 4 dx. And now we can integrate it. So we kind of covered, like 3 semesters worth of math tricks there.
Yep.
But do you feel good about those things? I mean, we can fit. Do you want to finish it? Shall we just kind of, maybe we should, right?
Would you hate me if I told you that I've been using, just to survive, I've been using the online derivative and integral calculators?
No, I mean,
Thank you.
Okay. I mean, I got to come clean and confess here.
no, look, you guys are math teachers. This is the way I approach it. You guys are math teachers. When I'm dealing with regular students, I don't know that I can trust them to gauge whether they understand something or not, right? You guys know how it is, right? They think they know it, but they don't, or they think they do. They think they don't know, But I figure you guys, as math teachers, know what it takes to classify something in your head as known, and sometimes it takes these other things to put it together. So, yeah, no, I'm fine with that. I figure you guys, math teachers, are struggling to understand because you know the value of understanding as opposed to just getting the answer. So sometimes there are multiple paths to understanding.
Yeah, I could. Yeah. Yep. Yep.
Okay, that's where I get, oh, because you're exponentiating both sides. Okay, never mind.
Yep, that's right. How about this one? You guys good with this one?
Yep. Because that right side goes e to the 4x times e to the c, right?
Yeah, just
Oh, yeah.
e to the 4x times e to the c. And so this is just some number, right? That's just some constant
Yeah.
anyway. So let's just call it.
Yeah.
But we have to go.
Yeah, that whole e to the c is just one big constant, right?
Yes, and so I've called it a new name, c sub 1, right? Just to be.
Yeah.
Some mathematicians would freak out, but it's just a constant. Call it what you wish. But the c sub 1 leaves a better paper trail for the changing nature of the constant. And once you're here, I mean, once you're here, you go back to y's, right? You know what v is equal to. V was equal to this guy up here, 4x plus y. So you're going to throw that in here and here, and you're probably done. There's not a whole lot of, I mean, you might be able to beat that to death, but one of the things that happens, beat it to death with algebraic simplification. But one of the things that happens is we reach kind of a point of enough is enough with some of this simplification. Because I don't know, I mean, yeah, I mean, you could probably take it, maybe you might even be able to take it all the way down to a explicit form of y, but anyway. All right, so the point of that one, again, just to remind you why we did that, is because we've seen one clear homogeneous equation.
Mhm.
And then and that was, close that up, come on. Anyway, the first one was clearly an homogeneous equation. And then, but then we wanted to show you this trap equation that it looks like it might be homogeneous, but it's missing the coefficients on the y prime. And so that's why we just do a straight up substitution. Kind of feels like a u substitution.
Mhm.
All right. Let's see, Carolyn, we'll kind of just bounce back and forth. Did you have some specific things you were looking at?
Well, I wanted to have pistols at dawn was number 37. I just cannot. This thing is driving me crazy.
Oh, that's the one that you were texting me about. And
Yes.
did you see?
So
Yeah, go ahead.
can I kind of tell you what I'm doing here? So do you want to write the problem down?
Yeah, give me 1 second. I'm trying to
Yeah.
adjust my interface. Come on, really? What do you do? Oh, that's it. That's the problem. That's the problem. All right, so let me get this another one here, another page. Yeah, okay, so 37, I've got it right here. All right, so this is a good example because this gives us the next kind of substitution that you were kind of exploring, Becca, here as cosine of x plus ln of y dx plus x over y plus e to the y dy equals 0. All right, so there we go. So talk to me, Caroline.
All right. So the first thing I did was label that first term with the dx as m.
Okay, yeah, so this
Cosine
one
of
here.
x plus ln of y. I labeled that m. And then I labeled x divided by y plus e to the x Is it e to the x or is it e to the y?
Yeah, that was your mistake. Remember, you copied it. You made it. You wrote e to the x, and
You know how many times I've done that?
well, I wish I could say that. I know the feeling, but yeah, it's e to the y, and that answered your original question.
I know, but it didn't really. Okay, so let's march through this if you don't mind.
No, that's fine. Let me talk
so-
about this one for a second. Let me just mention something here. Can I, before we get going on this?
Yeah.
Here is what we have. Let me give you. Let me do this right here. Let's do this without a safety net. See if I can do it without making a mistake. All right. Okay, so here's a different here is a differential equation, right? Equals 0. And it is, in fact, unless I made some silly little translational error here, it looks like it doesn't fit any of the substitution methods patterns in 1.6. But sometimes we get an equation like this and we can rewrite it like this, and then it fits into into the exact pattern that we want. It doesn't look at all like an exact, right? Especially if it comes to us packaged like that, right? We're like, what in the world's going to happen there? But if we remember that we can take this dy dx and split it up, so this is an aside. This is bonus material right here, not having anything to do with your problem. So I'm going to take that term and move it to the other side so it becomes negative, right? I'll just slide this over so it becomes negative, and then a cross multiply, right? So I get dy times xy plus e to the y equals negative cosine x ln of x plus ln of x dx, sorry. And then I can move that over, and all of a sudden we're right here. Okay, so I guess the reason I tell you that is because sometimes you'll see an equation that looks like this, and it can be rewritten to fit the pattern for the exact equation. Not a problem here because they already give it to us, but sometimes you'll see them like that. Anyway,
when you write it like that, the y's are on one. Well, you've got that x in there, right? So you can't just go straight into differentiation, can you? Because they're not separated, right?
Yeah, you mean the part that I've got circled, right?
Yeah.
Yeah. Remember, we couldn't just go straight into differentiation because you got y's hanging around on the right side.
Okay. Yeah.
And so, anyway, I don't know if you'll run into that. I'm just kind of looking ahead. I don't think you will. I think all of them kind of come to you ready to play the exact game, but they might come to you like this. Sometimes somebody might come up to you on the street and give you a differential equation like that, and you got to remember, I can split it out, and then it fits this m times dx plus n times dy.
Okay.
All right, moving forward, Carolyn.
Okay. So these exact equations, I'm losing track of when to take a partial derivative to respect to what, and then you take another derivative with respect to the other variable, and then you integrate and blah, blah, blah.
Okay.
So here's what I've done so far. So I labeled m and n, and then I took a partial derivative of m with respect to y.
Yes, that's right.
And then I took a partial derivative of n with respect to x. And what I got was that each partial derivative was 1 divided by y.
Yes. Yes.
Okay. So then next.
I'll write that down
Yeah.
here. Right?
Okay.
Write that down. I should have been writing that down. So the partial of m, and this is how I will always remember it, is, whatever this function is with the dx, right? You're taking the partial of that with respect to y. You just got to remember you're taking the partial with respect to the other variable. So
Yeah.
partial with respect to y is going to be the cosine x is a constant, so it disappears, equals 1 over y. And then the partial of n with respect to x is going to be 1 over y, and then e to the y, right, is a constant, so it disappears. Those two things are equal, so check. It's an exact equation.
Okay, right. All right, and then I took m because apparently you can choose either m or n. So I just took m as in Mary, and I integrated it with respect to x.
Yes.
Okay.
Yes. That's right.
So then I got sine x plus the natural log of y times x plus g of y, which is some function that we don't know about.
Yep, that's right. So
now, what I'm
go ahead.
Yeah, go ahead. Sorry. Go ahead and write out that.
So I was just going to say the important thing is the reason we integrate it is because m equals the derivative of our solution, this unknown function that we're trying to find. M is the derivative of f with respect to x. And so if you just integrate with respect to x, you should get the solution f, right? So that's why we're doing that. So as you said, sine of x plus the derivative, the integral of ln of x, what'd you say that was?
Okay, so the derivative of ln of y with respect to x is the natural log of y times x.
Yes.
All right, yeah, right. And then, okay, now, here's what I'm confused about. Why is that function that we tacked on at the end, the plus c, which we're calling g of y, why, if we integrated in terms of x, why is that a function of y?
Yeah, okay, so let me ask you this. Let me answer your question by asking a question here. So if I integrate, just say, we'll keep it super easy, 2x dx, right? What is, that is, of course, x squared, right?
X plus c.
Plus c. Why? Why do we put the plus c there?
Because it got grounded in my head in Calculus 1 that there's always a plus c.
Okay, so let's talk about that. So if I remember, when we integrate, what we're finding is the antiderivative, right? So the integral of this is this. How do I check that work? How do I know that this is in fact equal? How do I check that?
Take the derivative of the whatchamacallit, the integral.
Yeah, so that's the key. If you differentiate this, you should get what?
You'll get 2x plus 0.
Plus 0, right? Or just 2x.
Yeah.
So the integral, this after this equal sign, it could be an x squared. Why? Because the derivative of x squared is 2x. Or it could be an x squared plus 3. Why? Because the derivative of this is this. Or it could be an integral, it could be x squared minus 7. Why? Because the derivative of this is this. That's why we say it can be it can be x squared plus any constant. Why? Because the derivative of this is this. Okay, So that's why the C comes in there, is because when we differentiate to go back to the integrand, the C just disappears. So we know it's x squared plus something. We haven't been able to determine exactly what that something is. It could be any number, but it is going to be a constant. Okay? Now, back up to your so we're good with that, right?
Mhm.
Okay, now this is the key. To answer your question, it's critical that you understand this relationship right here. M is the derivative of this with respect to x. Okay, it's at the partial derivative, right, with respect to x. And so when you take the derivative of this guy, what do you get with respect to x? When you take the derivative with respect to x, the partial with respect to x, what do you get? Derivative of this is
Oh, cosine x.
cosine. What's the derivative of this with respect to x?
That's a chain rule, but right. So the derivative of the first times the second plus the first times the derivative of the second.
Now that will work, but we can make it simpler, because if I'm differentiating with respect to x, this is a constant.
Oh, right.
So
Right.
what is the derivative?
Derivative of x is just some whatever constant.
So it would just be
So
that.
like if it were 3x, the derivative would be 3.
Okay, so what is the derivative of x ln of y when you're differentiating with respect to x?
It's a well, I mean, it's ln of y.
Yeah,
Yeah.
because like you said, and that was a good way to approach it, the derivative of 6x, it's 6. The derivative of 10x, sorry, there we go. 6x is 6. The derivative of 10x is 10. So the derivative of ax is a.
Mm-hmm.
Derivative of ln of y times x is ln of y. Sorry, that's small there. But see, ln of y is just a constant when we're differentiating with respect to x, right?
Yeah.
Okay. So now, what's the derivative? Are you still with us, Becca? Is this helping you at all?
I'm with you, and this is good. I'm
Okay.
just following along.
So what is the derivative of this with respect to x?
A constant, right?
Okay, so what does this mean? What does g of y mean? It means it's an expression with just y's and constants in them, right?
Yeah. Y is the dependent variable, right?
Let me give you an example. You're right, it is. Let me give you an example. So g of y could be, come up with your favorite expression of y. 3y squared plus y minus 9. Or it could be 16y to the 5th plus minus 2y to the 3rd plus y to the 22nd, right? It's just going to be an expression
Function.
of y, right? That's the important thing, right?
Okay.
Now, so what happens when you take the derivative of this with respect to x? Okay, do this one. What happens when you take the derivative of this with respect to x?
Those go away.
0, 0,
Yeah.
0,
Yeah.
0, 0,
Yeah.
0, right? So it's the same game we did over here. So because we're differentiating with respect to x, we could have some random number of y terms at the end that we haven't been able to determine. And so we just say there could be some y terms. We'll just call it g of y.
Okay. It takes me a while. Like, I'm not the sharpest knife in the drawer.
Are you kidding me? You're doing just fine.
Yeah.
There are several moving pieces here, and the big one is that we're differentiating with respect to x, and so you got to remember anything with respect to y, or anything that's just a y term, is going to disappear. And so it's to put it another way, this term, that g of y, plays the same role that these constants played.
Right. So, okay. And it's g of y because we integrated with respect to x. That's why it's not g of x, because we integrated with respect to x.
Okay, okay, I'll talk a little bit and see if this answers your question, and then if not, you can hit me with it again, right? Let me ask you this. What is, let me see if I can do this here. What is the antiderivative of this? So if we're working with x's, doing this with respect to dx, the antiderivative of this is clearly sine of x every time, right?
Yes.
Okay, what's the antiderivative of this with respect to x?
With respect to x, so the ln of y is a constant. So it's right. I mean, I can see on the screen that it's x times, the ln of the natural log of y.
Let's change it. Let's just change it one little bit, right? Because I think this is
what I'm not understanding is that when you differentiate or you integrate with respect to the other variable, so if you differentiate x squared plus 2y with respect to y, so x squared plus 2y dy, the x squared goes to 0, correct?
Oh, differentiate, yes. So d y
yeah.
squared plus, what did you say?
Oh, wait, what, 2y?
2y. Yeah,
Right.
so that's right. So x squared, the derivative of that is 0 plus 2.
Yes. Okay. So how about the integral of x squared plus 2y with respect to y? So the integral of x squared plus 2y dy.
Okay. What do you think?
Okay, well, I mean, I just absolutely know that the second the second term is going to be y squared. I know that as sure as I'm sitting here. The x squared, does it go to 0?
No, see, you're differentiating.
Yeah.
Right? You're differentiating. This is anti-differentiating, right?
Yes.
So it would be
Okay.
x squared y.
Is it x? Okay, see, that's what I'm not getting a grasp on.
Let me give you this one. Let me just ask you this one. 6 plus 2y dy. What's that? What's the integral of that?
Okay, the second term is y squared. And so I guess the first term is it gonna be 6y?
Yep, that's right.
Where does that y come from?
Okay, let me ask you this. Let me answer. So
Oh, wait a minute. Oh, wait a minute. Okay, I think it's kind of maybe starting to come back to me. Yeah. Because if I were to integrate 6 dx, it would be 6x, wouldn't it?
yes, right.
Okay, I think I might have it.
Okay, so you got to remember this. Let me say this. The reason you know that this and this are correct is because the way you check your work when you're doing integration is by differentiating your answer. And so if you differentiate your answer, you get back 6 plus y squared. Okay, but this is not the end of the story, because there's a little hidden term right here. Plus 0, right? We're still doing dy. Okay, so what was the antiderivative of 6? 6y, right? plus antiderivative of 2y is y squared. Now, what's the antiderivative of 0? I don't know, but I know it's some constant, right? And so that's where the constant comes in, because we always have that plus 0 at the end of a integral, and the antiderivative of that is just that constant. How do I know that's true? Because if I differentiate this, I get this. If I differentiate this, I get this. If I differentiate this, I get this, right?
Yep.
So the moral of the story is, I can't exactly determine what exactly is the antiderivative of this, because there's this unknown constant that I have to live with. I have to live with a little unknown, right? And so for the same reason, when we have, say, this 6, let's see, let's do it this way. Let's go 6 plus y x dx. Okay. Let's see if we can do this one.
Okay, that's going to be 6x plus, is that going to be x divided by 2? I mean, x squared divided by 2, I'm sorry. Yeah, with that y there. Because it's a okay. Okay.
Right? Because we're differentiating with respect to x. This, and maybe, maybe if you just said this was ax, what's the antiderivative of ax? You see, oh, well, that's clearly ax squared over 2, right? The a doesn't bother us, right? In this case, we got to think of y as just an a, right? Just some. But again, we're not to the end of the story here, because there's this little plus 0, right? What's the antiderivative of 0 there when we're differentiating with respect to x?
C, right?
Well, certainly C would work, but keep going.
Well, any constant.
Any constant.
It could be negative 12.
Right. It could be negative 12. So it could be negative 12, it could be negative 7, but it could also just be a plain old y. Because why? Because when I differentiate this with respect to x, what do I get? 0.
The first week of classes, I had sent you an email asking you if C has to be a real number, and you said it does. So it could never be like the square root of negative 5. Is that what you're saying? When you integrate, C always has to be a real number.
Well, when we're doing so when we do integration in Calc 1, we're always integrating x terms with respect to x. Okay, we never do this cross integration. And so the answer to the question at that point, when you don't do a cross integration, it's just a constant. It's just a number, and it's just a real number, right? Like you said originally, it could be a 12, it could be a 7, it could be a 9, right? But when we're thinking about these as functions of x's and y's, and you probably only, well, yeah, when you think about them as functions of x's and y's, when you differentiate with respect to one variable, C could be a constant, but it could be all of these other y terms, because if I take the derivative of all of that in blue, it's just a big fat 0. Right? If I take the derivative of all of those terms in blue with respect to x, that's just a 0. The only thing I know for sure is that the antiderivative of this is this, The antiderivative of this is this, and then the antiderivative of 0 with respect to x could be just a bunch of y terms. And so I just say it could be some function of y, and that's why I write it like that. Because it could just be a whole mess of y terms that disappear when I take the derivative with respect to x. I don't know what they are at this point. Okay, and so that's where this comes in back up here. We take the antiderivative of this with respect to x. We're clean, no problem. This with respect to x, no problem. But then we could just have a bunch of random y terms. And we're at this point, we don't know what they are. We'll find them here in a bit. But at this point, we're just going to call them g of y.
Okay, got it.
That's some good stuff. Good questions.
Okay, so what I have is that the partial derivative of, what were we doing? And let's see. Okay, so what we got down to was that the integral of m was the sine x plus x times the natural log of y plus g of y.
Yes, that's always your second step, right?
Okay, now it looks like what I did then at that point was, it looks like I took a partial derivative of sine x plus x times the natural log of y plus g of y, I'm sorry. It looks like I took a partial derivative with respect to y this time. And I got sine x would go to 0.
Yes.
The natural log, the x times the natural log of y would go to 1 divided by y. And the derivative of g of y would go to g prime of y.
Sorry, did I get that right? Is that what you were saying right there?
Let's see, is the partial derivative of x times ln of y 1 over y?
The partial of just ln of y would be 1 over y, but x is a constant. X is a constant, so that's why the
So
x.
x stays there. Okay.
Let me
so
write
that
it like this so it's a little more clear. X times 1 over y, right?
Yeah, so that was my first mistake, I see now. Okay, all right. Plus g prime of y. Okay, now, okay, so because we decided that the partial derivatives were equal, I can set x times 1 divided by y plus g prime of y equal to n. X divided by y plus e to the y. Do you agree?
I agree with, we do set them to equal to each other. Let me tell you why we do that. But yes, this is the next step, okay? So let's kind of walk our way through this. Becca, you still with us?
I am. I'm here. I'm learning lots.
Okay, the key is this. This is this whole system is built on this fact that m is actually the partial of our solution with respect to x, and n is the partial of our solution with respect to y.
Mm-hmm.
Right? Those are the big keys, right? What is n? It's this. All right. Do we know what f is? Yes, look at that. We have found f to be this guy right here, right? We've got that far, right? From that step right there, we've found that much of f. Okay.
Yeah, okay.
The only thing we don't know is all the jumble of y terms that are possibly there. Okay.
Right. Yep.
So look at this now. The partial of y or the partial of f, the partial of this thing should equal this thing. Okay, that's when we say n equals the partial of our solution with respect to y, we're saying that the partial of, and I don't get disappearing ink when I need it. I have it when I don't. I don't have it. If I leave all that there, we're going to be in trouble. Sorry, guys. There. I think we can do that. Yeah. Okay. Yeah. So this is the solution. If we take the partial of it with respect to y, we should get that. And that's why we do what you just described. We take the partial of our solution with respect to y, and that should equal n.
Right. Okay. So because I made that mistake previously when I did not retain the x in that in that partial. So you remember I said, oh, it's 1 over y, right? Well, really it's x over y, or x times 1 over y. So then, now I got stuck, because now what I would do is I would subtract x over y from both sides, and that would go away. And that wasn't happening for me.
Okay.
So now we would get g prime of y equals e to the y. Do you agree?
Yes, that's exactly right.
So now we know that we need to solve for g of y, and we now have g prime of y. So now I would differentiate both, or integrate both sides.
Yep. So g of y equals the integral of e to the y dy.
dy with respect to y. Yep. So then that's going to give me g of y equals, and e to the y, because the integral of e to the y and the derivative of e to the y is e to the y plus c. Okay, now, but we're not, okay, so now the answer is, because we found f up above, if I could find it, there it is. So is the answer sine x plus x times the natural log of y plus e to the y plus c?
Okay, we are one strange little step from saying yes to that, because up to this point everything is correct, right? But this whole supposition, this whole process was based on the idea that our solution was an implicit function, an implicit equation. And so all we do is we take this thing that we just found, and you found it in every way correct, and you just set it equal to 0 so that it is an implicit equation rather than a function.
Oh, okay.
Yeah. And by the way, this should be a function of x, y here and up
Yeah,
above.
that's right. That's right.
Not a big deal, but
gosh. Oh, I have a real loose understanding of this. Oh.
Well, let's just you want to take a look at another one?
Yeah. Let's see.
Sorry, can I interrupt for a second?
Yes, please.
So earlier we were talking about the homogeneous, like that was that type of substitution. What is this kind of substitution?
Yeah, so this is what we call solving an exact equation, right? Solving an exact equation.
Okay.
And just real quickly, how do you recognize this? Well, it's not homogeneous. I mean, you can look right away and you can see, oh, look, I have no idea what the degrees of these terms are, and they're certainly not the same, right?
Right.
So it's not going to be homogeneous. And pretty much, if it's not homogeneous and it's not the basic substitution that we
like that one we did
before, you're kind of just left with hoping that exact is the method.
Okay.
But you can test right here. Step 1 is
right.
immediate quick test to tell if it's going to work or not.
Right.
Okay.
Okay, thank you.
Good question. All right. What do you think, Carolyn? You got another one on tap, or do you want me to grab one?
If you don't mind, how about you grabbing one?
Yeah. Let's take a look. We were doing what, 37? Should we just
That was
do?
37. That was unbelievable.
Let's just do 36. Or yeah, 1, 2, 3, 1, 2. Oh no. Let's do 34. Because this illustrates kind of a, well, either one. We'll do 34. So here it is. This gives us just some practice here at determining what we want to do. Okay. Okay, let's make sure I got that right. You guys can double check. Okay, Becca, you tell me what method I'm going to use here. Is this homogeneous? I guess is the question I want to ask.
No, it is not homogeneous because I can already see those first two terms that we have a degree of 3 and then a degree of 2 and
yeah, and that's the thing, right? Once that breaks down, then you know you can't use that homogeneous substitution. So we're stuck with hoping that it's an exact. So let's again, I think it's a smart idea to just, especially if you're kind of following the algorithm from the book, to make sure you quickly identify which one of those is M, and which one is N. Just to match what the book does. M is the one in front of the dx, and N is the one in front of the dy.
Is it not homogeneous because it's not linear, or is it not homogeneous because it's got, it's second order, or is it not homogeneous because it's mixed degrees?
Mixed degrees.
Okay. So you can have homogeneous second order differential equations.
Okay, now just to be precise, when we talk about second order differential equations, we are talking about an equation involving the second derivative. Okay.
Oh, so that doesn't have to do with the degree. Okay.
Right.
Oh, okay, gotcha. All right.
Yeah. So with homogeneous, the kind of combined degree of all of the terms has to be the same. And so we've got a third degree, a second degree. Everything stops there, but this is third, and there we go. We're no longer homogeneous. So let's check. Thank you. Check for exactness. How do we do it?
Take the partial derivative of m with respect to y.
Yep. So that's the first thing. You kind of take these cross partials. So the partial of m with respect to y is what?
Well, the first term is going to be y cubed divided by 3. No, sorry, 2y, right?
Keep going. You're not quite. You're getting closer. Warmer, I guess I should say.
Well, the 2x go. Does just the x go away? Is it 2y? Is it 4y?
Warmer. What do you think, Becca? Any thoughts?
I think it's 4xy.
Yeah, the 2 on the y squared, right? The 2 on this on the exponent comes out in front and multiplies times the 2x. So it's 2 times that 2x gives you the 4x times y, right? So that whole 2x terms just stays out there like a good constant coefficient. Is that okay?
Okay, so then it's the 3x squared that goes to 0. Is that correct?
That is right. 3x squared is gone. So we'll put that in there, plus 0. And then the partial of n with respect to the other one.
X.
What is that going to be?
4xy.
4x.
Mm-hmm.
Yep, that's great.
We're doing respect to x. Okay. 4xy, and then the 4y cubed will go to 0.
There you go. And so there you go. They're equal. And that says they're exact, and we should be able to go through our procedure.
Yeah, so we can later we can set either one of them to n or the other one to m, depending on which side or which term we integrate.
Well, here's what we're going to do. We're going to remember how we wrote m up top first. We're going to also now write this. This m is the partial of our solution with respect to x. And this n is the partial of our solution with respect to y. All right? And that kind of guides us through. So if you do reverse the order of these next steps, you got to make sure which one is a partial with respect to y and which one with respect to x. Let's do it the standard way, because I think the standard way should just work for us, and that is the way we've been doing it. We just start right away saying our solution f is the integral of, right, if you just integrate this with respect to x, which is m, right?
Mm-hmm.
Then you should be able to find, if you can integrate m with respect to x, then you should be able to find a f. So
But you could integrate n, right, if you wanted to. Like,
yes.
Let's say the integral of n were easier.
Okay.
But I mean, you could if you wanted to, right?
Yes, but what would you integrate with respect to?
Y.
That's right. That's the only thing you got to remember is all of that stuff switches.
Right. Yep.
And that's
okay. So we're going to integrate m. Okay. So we're going to integrate 2xy squared plus 3x squared dx, right?
Yes. With respect to x, yes.
Yep. Okay, so we're going to get x squared, right?
Mm-hmm.
Okay. The second term is going to be x cubed, but I got to figure out what's going to happen with that y squared on that first term. Becca, do you know how? Oh, did you already write it down? Okay.
Yeah, it just stays there. Because it's like a constant, right? Because we're taking it, we're dealing in respect to x, so the y is just like a constant.
The y squared is just like the 2, right? It just hangs out. We deal with the x alone.
Okay.
So you have the 2y squared by itself, and then you actually just integrate the x, is all you're integrating. Everything else you just kind of throw to the side, and maybe that's the way to think about it. Everything else just keep there and only integrate the x.
Okay, so now we have to take the partial derivative of that answer that we just got, right?
Yes, right. We've got, yep,
yeah.
that's right. So we're going to take the partial.
Yep.
With respect
and that'll be with respect to y, right?
Yep, that's right.
Yeah, okay.
Because we're about to set these two things equal to each other.
Right. Okay. All right, so with respect to y,
Let me write it just a little cleaner, right? So this is y squared x squared plus x cubed plus g of y.
yeah, I need to write that. I need to rewrite this. Okay, y squared times x squared plus x cubed plus g of y. Okay, now we got to differentiate that with respect to y. So that'll be 2y the x cubed goes away.
What happened to the x squared?
Yeah, I know. Why am I having such a hard time with this?
Well, it's not, it's okay. It's a little tricky.
It's just for some reason it's not cementing into my brain.
Let's do it this way. Let's just play some visual games, right? So this is what we're differentiating, right?
Yep.
So here's what I want you to do. When you differentiate with respect to a variable, I just want you to imagine that variable is highlighted, right? And everything else that is not highlighted is just a constant and just stays there. Okay? So all you're differentiating is that y squared, so that's 2y, and so the
Yep.
x squared just stays there, right?
Yes.
Okay? So that I don't know if that'll help, but you just remember that anything that is not being differentiated, you just keep it. And that's why,
Okay. Because it's attached, we have to think of it as a constant because it's attached through multiplication.
yep, that's right. I mean, it's the same as if I gave you this, if I gave you this problem right here, you would never have a problem with it all day long. What's the derivative of that?
6.
6. What's the derivative of 12x?
Yeah, I wonder if, okay.
And that's what you got to train yourself to
Yeah,
see.
exactly. And the reason the x cubed goes away is because there's no y attached to it through multiplication. And actually, if we treated that as a constant, it would be 0.
Well, right. What's the derivative of 5?
Yeah, 0.
Derivative of 7, 0. The derivative, we've kind of abused the notation, but the derivative of that with respect to y is 0.
0. Yeah.
Right? So that's what we're really doing here.
Right. So back to step 3 then. We've got the partial derivative of f with respect to y is 2yx squared plus g of y.
Yep, because the x squared disappears, plus g prime, right?
G prime of y. Yep. Okay. Now, earlier when we established that m equals the partial derivative of f with respect to x, and n equals the partial derivative of f with respect to y, well, we just found that to be 2y squared plus g prime of y.
Yes.
And it also equals 2x squared y plus 4y cubed. So we can set those equal to each other.
I love the way you said that because that's exactly right. It is also equal to this. We have two expressions for the same thing, and that's why we set them equal. And if we've done everything right, everything that has x's in it should disappear. That's the beauty of.
Right. Okay. So then we get g prime of y is going to equal, 4y cubed.
Okay.
Okay, I'm fighting with my pencil. Okay. Okay, so then now we're just going to integrate that to get g of y with respect to y.
Yes.
So g of y is going to be, oh, good. Look at that. It's going to be y to the fourth plus c. Okay, and then we're going to go back up and sub in g of y. Where do we find f? Let's see. It's going to be y squared. Well, let's go like this. I think I tried to mess things up.
I actually made it more complicated because we really didn't need to write all of this in there.
Yeah, but it's helpful. It's helpful.
Yeah.
Okay, so let's go like this. Let's say that if you'll allow me to rewrite that, you've got that thing highlighted where it's plus g of y over on the right-hand side of your screen.
Yes.
So if you'll let me rewrite it as x squared y squared, just because I like it better.
Yeah. Yeah, that's just fine.
X squared y squared plus x cubed. That x cubed should go in front.
Yeah, that's
Plus, now we just found g of y is y to the fourth. That should go in front. Plus c equals 0.
plus c equals 0. That's right.
So a mathematician would really like to see that written as y to the fourth plus x cubed plus x squared y squared plus c equals 0. Is that true?
When you get these polynomials of mixed terms, there's way less desire to put them in descending order. So
okay,
it's yes, probably but at this point, a lot of mathematicians would say, "I'm done. There's the answer. You figure it out."
Okay, so nobody's going to throw a hissy fit. Okay.
No, right. Not a problem.
Okay, so this has been super helpful. But what's going to happen is tomorrow morning I'm going to wake up and have kind of forgotten some of it.
Hey.
You know why? Because I'm like a basketball player. I have to throw 100,000 free throws before I get any good at it.
You know how math is learned, right? That's what
Yes.
we do. We keep building those connections, and sometimes it takes a while to build them. So,
okay.
So the trick is to keep working on the connections, right? Keep fighting for them.
Yeah.
And by the way, I'm recording this.
Yeah, we're a little disadvantaged because we're doing this in 7 weeks, whereas the kids would do it in 16, wouldn't they?
Yes, but we've kind of changed this to accommodate that because yeah, but yes, it's still tough. It's still tough. So there's no shame in filling, it's new stuff. It's different stuff. It's a little confusing. It's all good. You'll get it figured out, but it does take a little bit of effort. Yes.
Okay.
So let me just ask you this real quick. Like I say, I'm recording this, and assuming things are working, would you either of you, since you are the principal players in this, care if I posted this for the class to watch?
Did I say anything scandalous?
No.
Becca could tell us that. I think you were just fine. Yeah.
I think this has been derated. I think we're
I
okay.
don't have a problem with it.
I'm fine if you post it. I'm fine. I think that's really helpful. And if you did this with somebody else and they would let you post it, that's helpful for all of us.
Yeah, normally we would be meeting a couple hours two times a week, but
I miss that.
Yeah. It's a different ball game. So
yeah. Okay.
Is there any chance I can get one more problem before we go?
Of course. Yeah.
Number 43. I think throwing in that extra variable, I'm getting lost.
Did you say 43?
43, yep.
It's a reducible first order. When you kind of understand it, it kind of gets a little fun.
Well, I'll be excited to reach that point.
But it's There were 3 difficult concepts in this one little subsection of this chapter.
Yeah, that's what I was telling Beck at the beginning. This is a weird section because there are like 4 different sections in this one section. So that's why I split it up and made it double value. I don't know. Anyway. Okay, so yes, this is a second order equation, right?
Yep.
We got the second derivative there, and we have 2 kinds that we can reduce, right?
Yep.
The first
Yep.
kind are the second orders that, well, this kind of tells the story. The second order equation that are missing, they have an x in them, or they have some x's in them, they have y prime, and they have y double prime. And that is this one, right?
Yep. So it's missing just a y. Is that right?
That's right. It's missing the y itself.
Mm-hmm.
Okay. So the way to do that, did you already run through this a little bit, or
I have played with it. So I know like the goal, I would say p is equal to y to the first. Yeah. Yep.
yeah? So p equals y to the first, so that means y double prime is equal to the derivative of, right?
Yes. Yep.
Okay. We all good with that so far?
Yep.
Okay. Now, so we're trying to find y. Y is the solution. So this is the key right here. Y itself is equal to the integral of y prime dx, or in other words, the integral of p,
P. Okay.
right?
Yep.
So we're just going to integrate, well, there it is, right? If I integrate y prime, I should get y. So I'm going to integrate p. Okay, so do we have that right? Yes. Okay. How are we doing on that so far?
Wouldn't it just be
Wait a second.
P?
Yes, sorry.
No.
Yeah.
Go ahead.
Okay.
Sorry, I added an extra
You're
sprinkle
okay.
in there.
I'm following.
Okay. Now we're going to have, well, just following along here. P itself is going to involve one constant, and then we'll have a second constant floating around here. We'll see those come into play here in a second. Okay. All right, so let's make the substitution. So what does this become when we make these substitutions right there? What does our differential equation become?
It becomes xp to the first. I don't know what you call that.
Yes, x
P to the first. Oh, yeah. We could do it that way.
dp dx, right?
Yep. Is equal
Equals
to dy dx. Is that how we would
is
write
equal
it?
to dy dx, which is p, right? We're trying to get rid of the y's is the idea,
Oh, okay.
right? You're trying to get rid of the y's.
Okay.
Okay.
I'm good with that.
And now this is a new differential equation, and we have to decide, okay, how can we solve this particular differential equation?
And this one looks like we could easily separate. Yeah.
Yeah, it should be separable, right?
So you would have p dp on one side and 1 over x dx on the other side. Is that right?
How about dp over p, right? Is that what you
Oh,
said?
yes, that's right. Yep.
dp over p, and then the dx over x, right?
Mm-hmm.
Dx over x. Okay.
And then we integrate.
And then we integrate. So that's going to be ln of p
Mm-hmm.
equals ln of x plus
Mm-hmm.
c, right?
Mm-hmm.
Okay, and we can do the thing that we always do. We don't like having a lot of natural logs around, so let's just make them one natural log. Right?
Okay.
And then we'll exponentiate both sides.
Okay.
Which leads us to this. Absolute value of p over x equals some constant.
Okay.
Or if we get fast and loose with things, p equals constant times x. In other words, if we kind of ignore that absolute value. And we can do that because a lot of times we'll just require everything to be positive, so the absolute values are redundant.
Okay.
Okay, so, but notice we've got that c sub 1. That's a real constant, right?
Right.
But I don't want to know what p equals. I need to know what y equals.
Okay.
So what do we do now?
You got me. Caroline, help.
Okay, so we earlier established that P is going to equal Y prime.
Okay.
And, you know, I'm kind of trying to figure out which notations I like best, whether I like Y prime or dy dx. So I think the way I would write this is that I'm going to replace P with dy dx. dy dx equals C1 times x.
Okay.
And you
we're trying to find,
that. Yes, go ahead.
I'm sorry. And we're trying to find y, right? Okay, so I think then at this point, so dy dx equals c1 times x. If I'm trying to find y, I think I'm going to differentiate both sides.
Integrate.
I mean, integrate both sides.
Yes, that is right.
So then why, but then okay, keep going. Because then I'm feeling like y is equal to the constant.
C1
No.
X squared divided by 2.
X squared divided by 2. Yep. I was going backwards. Okay.
Plus C2.
Oh. Yep.
And see, we're going to get really cavalier. We're just going to call this c sub 3 x squared plus c sub 2.
Wait, pause right there.
Okay, so you're wrapping up.
How'd you get that?
You're taking that c sub 1 divided by 2. Let's write that down, right? And you're going to call that guy c sub 3?
Yep.
No, because we don't know what that constant is, so it's just a new constant.
Well, yeah, because c sub 1 can be anything. That means c sub 1 over 2 can be anything. So why not just call it its own constant and make things a little simpler?
That makes sense.
It's the same game as this, right?
And that's where, like in the back of the book, they got ax squared plus b. Their a just represents some constant.
That is
B
correct.
represents a constant.
Yep, that is correct.
That makes sense.
I'm surprised they would switch to a plus b, but you know math books.
I know, sometimes I listen to them and sometimes I don't.
So yeah, I mean, if these constants we just roll everything into the constant that we can, right? That's what we did. That's what we did right here. And you know, e to the c is just incredibly way more complicated than we need. So let's just but it's still just a constant. So let's just call it a constant.
Let's see. Now, does it matter when I'm going through? Is it more just for notation that you represented, like c sub 3 represents a certain constant and c sub 2 represents a different one? I mean, if I just put cx squared plus c, is that not okay?
That would not be okay because because that says that they are the two same things. They both equal 5 or they both equal 7.
But as long as those are two different, like if I had c sub 1 x squared plus c sub 2, that doesn't matter? Or does it matter that we kind of go in order?
No, it really doesn't matter. It does not matter just as long as you've got two separate distinct identifiers. And
from my understanding, it's convention that, you know, one will equal A and one will equal B. It just seems from other videos I watched, it just seems like that's just the convention that A and B are the chosen variables.
Yeah, and most of the time it doesn't matter unless you're trying to establish what those two constants represent. Like so, like in the position equation, the first constant you get, you know, is the initial velocity. The second constant you get is the initial position, and so you it's kind of important that you keep track of them. But in something like this, just whatever you want to call them is just fine.
And I like that. I think I just sometimes when I get going on my own in this, I don't keep track of as well. But
Well,
I understand that they're two different things, and I understand that they came at two different times. And I need to get better at that, but
well, and yeah, that's it. That's it. But you know, they do. There is some, you know, you can kind of do what you want there within, you know, call them what you want.
mm-hmm.
I had one professor back when I was going through school that used K's, and he always wrote them like this. Well, that's not a good, you know, he always wrote them like some sort of weird R, and you know,
They
I don't
didn't
know,
know.
but that was his constant.
Gotcha.
So yeah, so great question, because that gets us now you've seen all four different kinds of reduction.
Mm-hmm.
And you can kind of see, you know, some of them are easy to tell, or of substitution, I should say. Some of them are easy to tell from the others, but you know, you still have to get an eye for it, and it takes just a tiny bit of practice. But.
Okay. Man, I feel so much better. Thank you for doing this.
Well, thanks for asking the questions, right? I mean, I never know how you guys are doing out there in learning land unless I hear something from you. And I'm happy, you know, I'm just as stuck inside as anybody else, so I'm always excited to do something different. So I'm always willing to help if you've got questions.
So next we move on to, was it population models, or what was the next 2.1?
Yes, population models 2.1.
Okay. Okay.
Which we explored a little bit, but this gives you, you know, this gives you something to do with your differential equations, which is kind of interesting. But yeah, and we gotta have a test here. I'll probably try to get some information on that to you guys in the next day or two.
Oh, is that entirely necessary?
It will be painless, hopefully.
Oh,
Moderately
How many tests are you
painless.
going to have, Dr. Burr?
2. We're going to have one that covers the differential equations part and one that covers the linear algebra part.
Okay, all right. Okay.
So I may, and they're going to be take home. They're going to be open book. So I just want you doing some more problems, you know.
Right, okay.
So anyway.
Awesome.
Well, okay, I will.
Dr. Brewer, really seriously, this has been a massive help for me.
Me too.
Good. Well, you guys had great questions, and I hope everybody else will learn from these, and I hope they will ask questions if they've got them. But yes, thank you for asking your questions. And I don't want, you know, we go so quickly through this that I understand the pain of it. But if you will keep asking questions, I'll keep answering or trying.
Perfect. Thank you so much.
All right. Have a good night.
You too.